If I study general, yabba dibby 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 dum, all day long I'd NIPV PMT FV PPY CPY. Oi! Welcome everyone to this wonderful chapter 6 on financial products. The topics that we're going to learn in this chapter are significant to all of us. For a number of us, we'll be lucky enough to save up a deposit and buy our own home eventually, and make regular monthly mortgage repayments. And the other concept that we're going to look at is superannuation, or an annuity, which touches on all of our lives. Throughout our working life, we work, we pay money into super, and then we get paid back our super when we're in retirement. So let's dive in and learn some more. Today's lesson is about introducing financial applications. And to me, this is going to be one of the most valuable lessons of the chapter, because I've taken all the key concepts that you're going to be learning throughout the chapter: recurrence relations, the different types of financial products, the financial solver, and amortization table, and I've put them into one lesson to compare and contrast them to help you learn them and review them. So this lesson, if you can get your head around it, will basically help you understand pretty much all the concepts for this entire chapter. I recommend that you get a pen and paper and write some notes, because I'll be asking you some questions about some of the things in the early part of the lesson. And if you get some notes and learn this on well, you will be flying. We're going to look at 3 key skills that are often done separately under each financial product, but by comparing them, it will hopefully give us a better understanding. In our first key skill, we're going to look at recurrence relations for financial products and use that to help us understand the difference between our financial products. We're then going to look at the amortization tables and then a basic overview of how to use the finance solver. All right, the first financial product we're going to look at is an amortizing annuity, and we're going to understand it through its recurrence relation. Let's jump into this recurrence relation and see what it can tell us. V0 is $500,000. This means that over the course of someone's working life, they've saved up $500K. $500K is a decent amount. Either they've had an above average salary or they've been making extra repayments during their working life. Either way, well done. Let's work out V1. How much would be in this financial product, what the balance would be after 1 month. Okay, so V1 equals $1.005 times $500,000. Now, if we just work that out, it would equal $502,500. What does this 1.05 mean? This is the interest that is being earned on this money. So you've put $500K into this product, into your super, and every month it might gain a bit of interest. So after 1 month, oh, wow, it's grown with interest. Your value is now worth more. But what's happening? We're also minusing $3,220, because when you're in your retirement, you need money to live off. So the money is coming out of this financial product and it's being paid to you, and you use that to fund your lifestyle. So what's the net impact of this? It did rise with interest. It did fall with the payment. How much is left afterwards? $499,280. So you're left with a little bit less than what you started with that month. And that's how these annuities work. Eventually, they're going to drop down to 0, but they're going to last long enough to fund your entire retirement. Let's just confirm this and see what happens after the second month. All right. We take the balance that was in our annuity, which is $499,280, and yay, it gets a bit of interest. It grows to become $501,776.40. But then it's making that regular payment, $3,220, so it becomes $498,566.40. Sweet. Okay, can you see what's happening here? If you can look at this recurrence relation, understand what's going on, what each of these numbers mean, you're going a long way to understand these financial products. The 1.005, that's the amount it grows with interest each month. The minus 3,220, that's the payment that comes out to you. Cool. So that's why it's called an amortizing annuity. Annuity is something that's making these regular payments to you in retirement. The word amortizing describes a process of gradually dropping down to 0. Eventually, this thing's going to hit 0. These are some notes to summarize those key ideas. We're going to look on to the next financial product. All right, now we have something called a perpetuity. Now this, if you look closely, will look exactly the same as the annuity, with one small change. The number of this payment is different. And it's not just that the number has changed, it's that it's changed to a very specific and special value. To understand what's going on over here, let's work out V1, okay? The scenario is the same. Perpetuity is the same, is a type of annuity. So it's still you've saved up money, or you've put money in a financial product and it's going to make payments out to you in your retirement. Perpetuities can also be like scholarships. A university might pay scholarships to people like $2,000 to the best student in dentistry every year. And that could be because someone's put a lot of money into a perpetuity in honor of their grandfather. So anyway, what's happened? Someone's invested this $500,000 either in their super or they've given it to the university to make payments. After 1 month, it grows with interest, times this by 1.005. And if we remember from last time, what did that become? It became $502,500. Then, okay, yay, it's grown in interest, but it still needs to make its payment to the person in retirement or to the scholarship recipient every year. It makes its payment, and this time the payment is $2,500, which is exactly the same as what it grew by. So what's it going to become? It's going to become $500,000. Wow. Hang on. What's going on here? Let's work out another payment. Let's do another month. 1.005. All right, what's the balance now? Oh, it's $500,000. Can you see what's going to happen? It's going to grow again to 502,500. It's going to drop by 2,500. It's going to stay at $500,000. This is why it's called a perpetuity. Perpetuity from the word perpetual. It lasts forever. Either this person had enough money to put in that the interest could balance the payments, or the payments were small enough that they didn't actually drop the principal at all. If you have this in your retirement, you can get this $2,500 every month, and then, you know, if one day you die, you can pass on your $500K to your kids or to your grandkids. This university can keep paying the scholarship forever and ever. So if you're lucky enough to get one of these products, or if you're disciplined enough to only spend $2,500 every month, you can actually be left with a decent sum at the end. That's a summary of the key idea. All right, let's look at the next product, a reducing balance loan. And hopefully you're making some notes about the difference between these four things. It is a lot to remember, and we're definitely going to go over them through the rest of the course. But if you can get like a good summary of them now, wow, you're doing really well. All right, let's look at the recurrence relation here. If you look closely, you'll note it's exactly the same as what we had for the amortising annuity. How does that work? Two different financial products, both with the same recurrence relation. Mathematically, nothing's changed. Mathematically, nothing's changed, but conceptually, or in practice, something has. The payments are still the same amounts, but the direction they're going from and to is different. With an amortising annuity, you gave a chunk of money to a super fund, and then you received regular payments. For a reducing balance loan, an institution, not the super fund in this case, a bank, is giving you the big chunk of money, right? This $500K actually comes to me. Yeah, I've got the money, I buy a house. And the payments, I pay to the bank, right? I give it back every month. The payments aren't coming to me in retirement. The payments are going from me to the bank. So that's why the numbers are all the same, because the sum of money that was here is the same as what I gave there, and the payments that were coming this way are the same as the payments that are going that way. It's just the roles are reversed. So let's see what's happening here. I take out a loan of $500,000. After 1 month, this $500,000 gets multiplied by 1.005. What's that? That's interest. The bank is charging me interest. They're charging me a fee for having given me the money. Okay, right. So I previously owed $500K, but now the bank's given me an extra fee. I owe $502,500. I have to pay back more. So what I do is I make a regular monthly payment of $3,220, and that allows me to drop the amount that I owe, right? Because my payment is bigger than the interest that was added, I actually reduce the principal. And if I do that again, I'll be able to drop it even more. All right, so right now at the end of the second month, I owe $499,280. All right, I get charged interest. That becomes $501,776.4, but I'm going to make my monthly payment. I'm going to make that payment, and I'm going to drop my balance again, $498,556.40. So after 2 months, I've made 2 payments, and even though there's been interest added, I've been able to drop it down lower. And if I can do that for the rest of the term of the loan, for all, usually let's say 30 years, eventually I'm going to get it down to a nice big fat 0. Cool. Is this making sense? Are you getting a hang of how these recurrence relations tell us the story of the financial product? What's this thing called an interest-only loan? Okay, it looks mathematically the same as a perpetuity. Again, we have the case of a loan. I get $500K from the bank. Let's see what happens after 1 month. 105. You're getting the hang of it now. What's that going to equal? $502,500. Oh, I've gone up with interest. I make my payment, and I just stay at $500K. I haven't actually paid off any of the principal. So I do it again another month. I have my principal. I owe $500,000. It grows again to $502,500. I make the payment. That's only worth the interest that it grew. it just stays at $500,000. I'm never going to pay it off. I'm going to have to pay this for the rest of my life. These things are considered a risky financial product because you never pay back the principal of the loan. 30 years later, you still owe $500,000. And that can be a risky situation to be in. And that's why we call it an interest-only loan, because you're only paying the interest. All right, our last financial product is something called a compound interest investment. Let's see what's going on here. Look at the recurrence relation and notice there's one thing that's different to all of the other ones we've looked at so far. What's the difference? That's a plus there. That's a plus there. This payment is doing something different, okay? We're investing our money here. Right? I'm putting the money into the bank or any kind of investment product. So I start off with investing $500,000. After 1 month, I get interest. Yeah, because bank accounts can pay you interest. Okay, if it's not a loan, if it's an investment, the interest works in your favor. And that's going to grow, as we all know, to $502,500. And what I'm doing is I'm taking it from my salary, my earnings, I'm going to add in some more money, right? Not only do I want to gain the interest, I want to get my thing to grow even more. I'm adding $3,200. And if I do that, I get to $505,700. Wow, so my investment's growing a lot. So what happens with the second payment? Well, we're earning our interest, but we're now earning interest on $505,700, i.e. both the interest we earned from last time and the payment we made. So we get to, like the payment we made and the interest, both are going to grow more. And not only that, we're going to add in another payment as well. So we're really getting a lot of money. If we drew a graph of what this looked like, it would look something like this, right? Zoom, our value is going up and up and up. Why is it called an annuity investment? Because this is what's happening when we build our superannuation over our lives, right? We work, we have money in our super, and we add to our super every time we get our salary, every month or however often we get it. So over the course of our working lives, our superannuation is going up like this with this compound interest power. Then when we retire, we get our amortising annuity that goes down. So actually, we can sort of look at this graph as two processes as part of superannuation. This is the annuity investment, or the compound interest investment part. And this is the annuity that amortizes, right? Some people call it an amortizing annuity. Eventually it drops down to zero, and that's when we are retired. And that's when we are working. Does that make sense? All right, here's an awesome summary of all those key ideas. Which ones are loans, which ones are investments, what happens to the balance over time, when the payments come from you, when the payments come to you. Have a read of that. See if you can tell the difference between each of these 5 products, and keep that in mind as we go into the next questions. All right, how's it going? You've learned like 5 new financial products. That's a lot to take in. And what are all these definitions and terms and this way and that way? But take a deep breath. In this lesson, we're going to cover all the key skills for this chapter. Take a drink of water and let's dive back in. All right, so if you understand a recurrence relation, then you understand automatically an amortization table. They're saying exactly the same thing. We started with a balance of $500,000. That's what this table is telling us. Then we knew that we grew to $502,500. Yeah, up with interest. What's happening there? Oh, look, that interest was $2,100. That's what we added. Then we dropped $3,222. I've made this table slightly different to the previous example, but go with me. The idea is still the same. And oh, cool. Yeah, that led to a new balance, right? There's only one extra column here that tells us the difference between the old balance and the new balance. That's the principal reduction. Like the balance, another word for balance is principal. We can keep a balance with that. The tables show some cool things because it really helps you just see all the things that happen as a loan in one clear image. We can also see that for this amortizing annuity or this reducing balance loan, the value has dropped down to 0 over time. And the last sort of key idea is that on the side we have the number of payments or the number of months that we're in. So if I have 300 months in total, I can say, oh, well, that's 300 over 12. That's a 25-year loan. It's a 25-year retirement package. All right, so I understand what this table is telling us, but let's go over a few calculations just to reinforce how we could find some of these numbers if we weren't sure. I want to calculate the interest in this row here. I'm told that my amortization table is a reducing balance loan, and it's 6% per annum. Okay, so these payments are interest. I'm making them they're being added to my loan. They're making me owe more money. How do I work this out? If I'm doing 6% per annum, then I want to work it out monthly because each row is a month. So we'll go 6 divided by 12, right? I need to convert that to a decimal to make it into 100. And then I want to multiply that by my previous balance. So this balance here is showing what happens at the end, after we end up with interest, after we drop with payment. This one in the previous row is like the balance that I'm calculating the interest on. So 4,99278. If I do that multiplication on the calculator, 6 divided by 12 divided by 100, times that, then I will get 2496.39. Nice, that's where our interest payment comes from. What's this principal reduction? Okay, well, let's do a little quick image. We have the balance of our loan. Eventually, the balance is going to hit a nice fat zero. At the end of each month, we go up with interest. That's our interest. Then we make our payment, right? That's our payment. And the difference between them, the payment minus the interest, that's going to be our principal reduction, right? Because that's the difference between the old balance, like balance number 1, and balance number 2. And if you look at the table, you'll see those calculations. The principal reduction is the total payment minus the interest. The difference between the first balance and the second balance is the first balance minus the principal reduction. All right, so can you see that by comparing these amortization tables, we're actually getting a better understanding of what these different financial products represent? And hopefully, we're also getting an understanding of the amortization tables themselves and the recurrence relations, and we're building a large picture, one that's hard to hold in our heads, but hopefully really, really helpful. The last key ingredient to add to it is the financial solver. Okay, and the key idea behind the financial solver is the difference between a recurrence relation and a rule for the nth term. If you think back to our last chapter, for every product, like every kind of depreciation or flat rate, unit cost, compound interest, simple interest, we sort of defined a recurrence relation, and then we defined a shortcut rule for the nth term. The thing here is that when we have both a multiplication and an addition or a subtraction in our recurrence relation, it's impossible to write a rule for the nth term. So far, if you look at all the other recurrence relations we had, they were all either arithmetic or they were geometric recurrence relations. This one that's an arithmetico-geometric, it's got both the multiplication and the addition or subtraction in it, has no rule for the nth term. But we don't want to have to write out like every step of the way if I want to know how much I owe in 30 years' time. With computers, we can shortcut these methods, and so we use a computer, our CAS calculator, to predict ahead. This financial solver is a replacement for the rule for the nth term. Does that make sense? Cool. There are 7 entries we always have: number of payments, interest rate, present value. You know these, you're going to see them, you can read them. We're going to apply them to some examples. The key idea that I want to emphasize is that anytime you receive money, that's positive. And anytime you give money, anytime money comes away from you, that's negative. And that idea is hopefully going to help us understand always what sign to put with our numbers. All right, let's do an example with this finance solver. We've got Morty, he's taking out a 30-year reducing balance loan, $350K. We've got his interest rate, we've got his payment. We're asked to find how much he owes after 20 years. Now, we can't do that with a recurrence relation because a recurrence relation is like 20 years by 12 months. That's 240 months. That's a lot of calculations. And I can't see the answer in my table, like that row is hidden. So we need our finance solver. TI Inspire people, you're going to get the hang of this very shortly. Menu 8.1, ClassPad friends, you're also going to get the hang of it. Go to your menu, scroll across 1, hit financial, and then press compound interest if you have the choice. Okay, N is the number of payments, okay? And because everything's happening monthly, we need to do the number of months. So we can just write here 20 times 12. We don't have to calculate it ourselves, just do that. Then press tab to go between the cells. It's a fast way to do it. Interest rate, 3%. Put in the annual interest rate, don't change it to monthly. All right, PV, that's the present value. That's like what happens at the beginning. Morty is taking out a loan of $350,000. So it's $350,000 as the number. We ask ourselves, will it be positive or negative? And these are the questions we're going to ask ourselves every time, and they'll change depending on the financial product. If Morty is taking out the loan, he is receiving this $350K to buy the house. So it's a positive 1, 2, 3. Nice. His payments are $1,475, but he is making those payments. Those payments are going away from him, so that's negative. Does that make sense? He's losing the money when he makes the payments. Negative. The bank gets the money. If I was the bank, I'd make it positive. I'm not the bank. All right. Future value. If it was the end of 30 years, it would be 0. we've put in 240, so we'll get to that in a second, but PPY is payments per year, it's 12. CPY is compounding periods per year, it's 12. They're always the same for us. Let's tab back to FV. We press enter on new, and voila, 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 we have this value here. Now, why is this negative? There's always a reason behind the positives and negatives, because at that point of 20 years, I owe that money, right? If I was to close up a loan at that point, I would have to give that money to the bank. That money doesn't belong to me right then, it's how much I owe. So that's why it's negative. That's the reason why the calculator gives it to us. If we're asked how much does he owe, then we would give our answer as a positive value. All right, these are all the key ideas from today's lesson and pretty much all the key concepts you need for this entire chapter. We've got our recurrence relations, we've summarized the different types of financial products here, we've got our finance solver, and we've got our amortization tables. Take this knowledge, use it well. In our future lessons, we're going to do some more nuanced examples, some more complicated examples, but we're going to apply these same principles again and again. I'll see you next time. If I study general, yabba dibby 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 dum, all day long night, NIPV PMT, FV PPY CPY, why? Gotta get to my financial goals. Gotta study general maths. I'm reducing balance. Welcome everyone to today's lesson on reducing balance loans. We're going to look at the key skills, which are the recurrence relations, the amortization table, and the finance solver. A little bit more depth to last lesson's overview of all of our products. And in our next lesson, we're going to look at some of the tough reducing balance loans questions that often throw students up. All right, let's start by looking at the recurrence relation of a reducing balance loan to help us unpack and understand what's going on. Now, it's a loan, so we're taking money from a bank. We're using it perhaps to buy a house. To understand the process, let's look through how the recurrence relation works. We'll calculate V1, which is going to be the value, the balance, the principal of the loan. All those words basically mean the same thing after 1 month. So we have 1.005, and we're multiplying it by $500,000. Now, if I just worked out what that calculation would be, it would be $502,500. Okay, so what's that? That is the amount of money that I owe. We're continuously, in the reducing balance world, continuously calculating how much money do I still owe to the bank. So at the end of the first month, I'm charged interest. The bank is giving me a fee for letting me borrow the money. Oh, you're now having to owe $502,500. Then I come along and I say, I'm going to make my monthly payment $3,222, and that's going to drop my principal down. It's going to make it worth $499,278. And that's basically what's going to happen every single month. The bank's going to charge me a fee with interest. I'm going to owe more, but I'm going to pay more than that, and I'm going to drop it down. And if I do that again and again and again, eventually I'm going to drop it all the way down to zero. I'll just show you this idea for the second one. Again, with that second payment, we can see the interest made the balance grow, but we made a payment to reduce the balance of our loan. It's dropping more, it's getting lower and lower. Eventually, after, I believe this one's 30 years, 360 payments, we're going to get down to zero. V 360 will equal zero. That's a summary of the key ideas. Let's now practice this with some questions. All right, let's look at the amortization table for reducing balance loans. If you want to go over any of these concepts in more detail, you can also always look at the first lesson of the chapter where we covered recurrence, the tables, and the financial solver in a bit more depth. In this lesson, we're going to focus specifically on the reducing balance loans. And this table tells us the exact same thing that the recurrence relation did. We start with a certain balance. We're going to add a bit of interest. We're going to make a payment, and the balance is going to drop. Drop, drop, drop. Eventually, for a reducing balance loan, the balance drops all the way down to zero. We have here some formulas that we can use to help us do some calculations. We might draw on them in the coming examples. All right, but let's dive into it and see where some of these values come from and how to calculate them if we weren't sure about them. So for our interest payment, where does this $2,500 come from? Well, I'm told that my annual interest rate is 6%. But I know that each of the rows in the table represent what's happening every month. These actions, this interest increase, this payment, this drop of the balance, they're happening every month. In total, there are 300 months. That's about 25 years. So we take our annual interest rate of 6. We divide it by 12 because we're working on a monthly basis. And we divide it by 100 to make it into a decimal. We multiply that by the previous balance, the $500,000. Okay? The previous balance comes from the previous row. If we do that on the calculator, 6 over 12 over 100 times 500,000, we would get $2,500. Okay. Now, our principal reduction is the difference between our payment and the interest. What's going on over here? We have our balance, 1, our first balance. Eventually, it's going to drop down to 0. It's worth $500,000. We increase with interest, and then we make a payment, and the balance drops. So this amount here is our interest. This amount here is our payment. And we can clearly see that our principal reduction, the amount the balance drops by, like the new balance, balance 2, the difference between them is going to be our payment minus our interest. In this case, 3,222 minus however much went towards interest. And that makes sense from the examples we saw before. We owe a bit more, we make a payment to drop it down. That's where the 722 comes from. And in this little picture here, that is the principal reduction. Sweet. So we have our payment, we have our interest, we have our principal reduction. If you want to draw a new balance, right, we can run on those. If we want our new balance, we get 500,000 minus the principal reduction, in this case, 722, and that gives us our new balance. There's one other thing you might have spotted in this table, that while all the payments were exactly the same throughout all 25 years of this loan, in the very last row, the payment was a little bit different. And that's done to ensure that we get to exactly 0 at the very end. If you want to understand this final payment a little bit more, watch the next lesson where we look at some of the calculations and how to calculate this final payment. All right, let's look at the finance solver for reducing balance loans. Because of our knowledge of reducing balance loans, we can define some parameters we're always going to use in these contexts. So when I take out a loan, I am getting the money. It's coming to me into my bank account. I have a positive present value because it comes to me. When payments happen, who's making them? I am making them. They're coming from me to the bank. So they're negative. They're going that way. Now, a future value, if we go to the end of the loan, will be 0 because I've paid it off completely. But if we sort of pause halfway through the loan, say it's a 30-year loan, 20 years, and we stop and we go, all right, what's the deal? Who owes who money? Let's say I've got, I don't know, $100,000 left of the loan. I still owe that to the bank. Yeah, I still owe that money to the bank. And so it would have to come away from me, and it's going to be negative. So 0 is at the end. If we were in the middle, it would be a negative value. Cool, let's do it. All right, those are all the key ideas for reducing balance loans. There are some nuanced examples when we have changing conditions, when we have a final payment, and that's what we're going to look at in the next lesson. So those are really tough, advanced questions for all you go-getters. Got to get to my financial goals. Got to study general maths. Oh, those questions in this lesson look really hard. I'm reducing balance. Thanks, Edrolo. Welcome, everyone, to today's lesson on reducing balance loans, part 2. Today, we're going to be looking at some of those more advanced skills. Specifically, we're going to look at using the financial solver when we change our conditions, when there's sort of two things happening. And we're also going to look at this elusive final payment and how to calculate it. All right, if you're operating under changing conditions, if you had one scenario for your loan or your annuity, and then the conditions changed, maybe your interest rate went up or down, or your payments, you increase them or decrease them, or you change the term, the length of your loan, then that's going to have an impact on the second stage. And you're probably going to be wanting to use two financial solvers to solve it. Drawing a graph can often really help as well. Maybe you'll say, oh, the balance was dropping, then there was a lump sum payment. So then the balance just became here, and then dropped again. Visualizing what's going on can really help you understand. And these changing conditions are real world scenarios. Like if you've taken out a loan for a home, your interest rate will change over time. And if you want to make a lump sum payment, then you might also drop your principal too. So this really does reflect more accurately what's going on in the real world. All right, Fatima is borrowing $235K for 20 years at a certain interest rate. And after 4 years, this interest rate is changing. Let's draw a graph just to get a feel of what's going on. In this case, the graph is not going to tell us too much. There's not like we can't see the change so well, but it will give us an indication. All right, there's a loan. It originally looked something like this. She was going to be paying off the money, and at 20 years' time, she was going to get down to 0. At 4 years, right, at 4 years, The scale's not perfect, but the idea still works. Something's changing. Previously, she was doing, the value went up, she paid off principal, interest, principal, interest, principal, interest, principal. Now, the interest is going higher. Interest is higher. Her principal needs to be larger, right, to get to whatever the new drop's going to be. So our principal is changing. We have two stages. We have before and we have after, okay? So let's get rid of these guys, okay? And let's see what's going to happen, what we know about the before, and use that to help us work out what's going to happen with the after. All right, TI Inspire, menu 8.1, ClassPad, menu, scroll across, financial. We have a finance solver. It's a little bit going on here. I need to know how much Fatima owes at the beginning of this new period, from year 4 to year 20. I don't know her payments. I don't know her value there. So we might have to do a few stages here. In fact, this problem is going to require 3 finance solvers, okay? So let's first understand the initial conditions of the loan. Fatima starts with $235,000. And under the original plan, it was going to drop to 0 in 20 years, 20 times 12. And the interest rate was 4.8%. Using that, I can calculate value of the payments that should be paying. I can see that's too big. I put an extra 0 there. So we go down here. Her payments were, in this period, $1,525.05. Okay, cool. Now that we know what her payments were in that section, we can use it to find how much she owed at the end of the 4 years. So let's leave the payments there. It's nice because it has all the decimal places. And we're going to change our time period to be 4 years. Using that, we press enter here, and we can see that after 4 years, she owed $204,108.40. Okay, can you see how doing a finance solver under the first scenario can give you information that can help you for the second scenario? And how by drawing a graph, we can actually place the numbers in a logical way that helps us understand what's going on. We're now in a new world where Fatima owes $204,000 and she still needs to get down to 0 in 20 years with a different interest rate. So one step at a time. Let's change our future value, Control C, to be the present value, because this is now how much is being borrowed at the beginning of this loan, right? At 4 years' time, Fatima is kind of taking from the bank. She has in her bank account $204,108. Okay, she's going to now start paying off that loan. Her payments, we don't know. That's the thing we're trying to find out. Okay, the future value is going to be 0. 0. Okay, there are a few things that have changed. Her interest rate has gone up to 5.3%. And the number of payments now is, well, the gap between the 4 years and the 20 years. So she only has 16 years left. So 16 times 12. And using that information, we can press enter and work out the value of the new payments. Notice that throughout, I never rounded decimals until the very end. I always just Control C and Control V. And that's how we work out the new payments for this side of the cycle. And those were the 3 steps we did in solving this question. All right, how's your brain going? A bit stretched? Good. We're going to now look at another tough concept that a lot of students struggle with. And this is really, these are kind of the skills that separate the top students. It's called final payment. And what happens when we pay off a loan is that we have our balance, we have our interest rate, and we have our payment. And that payment is the same all the way. But often in the tables, you'll see that you get these like nice round numbers, $3,171 flat, not $3,171.02 or less, or $3,170.98, or even 98.76. If you want to pay off your loan exactly in 25 years to get exactly to 0, the regular payment's not always going to be a nice round number. Does that make sense? So in reality, the number is something like this, 3171.72563, or 12563. And then the bank just rounds it off and says, all right, make it 3171. What that means is that you've actually paid a little bit too much along the way, and your last payment can be less, right? When you get to your final balance. If you were to pay your full payment, you'd be paying too much. So that's where the idea comes from. We have to work out how much this is going to be. And the trick is that we don't want to just pay the previous balance, $3,046, because we're still charged interest, right? If we think of our recurrence relation, we still have the 1 point, whatever it was, I don't know, 036 multiplied by 3046.04. We were still increased by interest before we make our payment. So this number here is going to have to take that into account. There are two methods for solving it, and I will show them to you now. The first one is what I just said. We look at the balance prior to the final payment, we add the interest. And if we do that, yay, we know what our final payment should be. That's actually the method that I use because I find it easiest to remember. It makes logical sense to me. And when I think about it, I visualize this amortizing table. I think I want the previous balance, I want to add my interest, and that's going to give me my final payment. There's a second method, which is also works and is pretty cool. We're going to get into that a bit later, and I'll show you how it works there. All right, let me show you what's going on. 25 years, 12 months a year, 3.7. We're borrowing 621, 2, 3. Regular payments, 3171. Future value is 0, okay? If we wanted our future value to be 0, our payments should actually be $3,170. So we've actually paid a little bit, we're paying a bit over every time we make our payment. But let's say we were back in the 3171 land. Let's have a look. What would we owe before our final payment? Right, $299. Our balance prior to the final payment is $3,046. And you can see that in the amortization table over here. What if I did all 300 payments at $3,171? Then when I press enter here, notice that I've gone over, right? Usually, if we just go back one step, usually the future value is negative because we still owe that money. But if we stuck with our payments the entire way through, we end up having overpaid by $115. So that's a visual, well, a sort of a mathematical, it's a finance solver method of understanding what's going on, and hopefully that makes a bit more sense to you. How do we actually calculate this 3055.43? So what we're going to do is we're going to do the method 1, which was first calculate the amount owing just before the final payment. So that was our $299. Future value, we owe $3046. So before our final payment, we owe $3046.04. Now, I'm pretending that I can't see this table in front of me. Is that cool? I'm showing it to you so you can help, understand what's going on, but we're going to calculate this as though we didn't have the table, we just had this information, and we had to work it out ourselves. Okay, so that's how we've just worked out the balance prior to the final payment. Now I want to work out this interest rate, right? How much interest are we adding onto this balance before we pay it off? So we're told that we have 3.7% per annum. So if I go back to my calculations, I can do 3.7. If it's annual, I need to divide it by 12 to make it monthly, divide it by 100, and then I multiply that by the prior balance. Now I want to get all of my numbers. So I'm going to actually Control-C and Control-V this. Escape, Control-V. I can get rid of the negative, and we get the interest that is added to that balance just before our final payment is equal to, let's write the calculation, which was 9.39. Okay, does that make sense? That before our final payment, we've increased with interest. Now, to work out how much our final payment should be, well, we'll take how much we owed, which was this amount of money, and we're going to add the interest, which is that. We press enter, and our final payment is $3,055.43. Make sense? If that makes sense, then well done, because a lot of students find this really hard. Yeah? 2 steps. What is the balance prior to the final payment? What is the interest I have to add to that? That's how much my final payment should be. All right, let's have a look at method 2. If you liked what you saw in the previous slide, method 1, if it made sense to you, you're sailing. You don't have to watch this. But if you're curious about another way to solve it, or that sometimes is a bit faster, then you're welcome to watch. Okay. This method 2 relies on the idea that if we paid the same amount every time, we would end up overpaying by a little bit. We looked at that in the previous slide when we did this. We said if I did through all 300 payments at $3,171, I would overpay by $115. Now think about what's happening there. We got back to our second last balance of $3,046. The interest got added, right? So we added the interest there. That's already been taken into account. And then we paid this money. So if we've overpaid by $115, then we should have actually paid $115 less than what we actually did. Does that make sense? Let me show you that just so you can see what's going on. I can do Control C, right? I escape and I say, I'm going to take that 3171 that I had, and I'm going to subtract the amount that I overpaid. And look at that, $3,055.43. Let me write that down. 3171 minus 115.569 equals $3,055.43. And if we look back at our previous slide, that was the exact amount of the final payment. So this works in one step because the interest is already added in when we make the 3171 payment. And therefore, if we subtract how much we overpaid, we get what we should have paid. Cool, that works. How do we do this? We looked at that $115 using method 2, which I described over here. We calculate the balance after the hypothetical final payment of 3171, and then we work out how much we overpaid. In this case, we overpaid. Sometimes we would underpay because our payments were a little bit less than what they should have been, and then there'll be a slight calculation there as well. Okay? Personally, I like method 1 better because it works both when we just have the question, and it also works when we're given a table. But if you like method 2, then go for it. Make your choice. We're going to do a question now. All right, those are the key skills from today's lesson. There were some challenging ones, but if you can get your head around them, then you are doing really well. I'll see you for the next lesson on interest-only loans. If I study general, yabba-dibby-dibby-dibby-dibby-dibby-dibby-dum, all day long I'd NIPV FVCPY PPY. Oi! What's this in front of us? Whoa, looks dangerous. Why is this dangerous? And what is it? Well, it's an interest-only loan. And just to demonstrate the danger of interest-only loans is we have here a report from the Australian Securities and Investments Commission, ASIC if you remember, and they, back in 2015, did an investigation into the banks and what they were doing with the interest-only loans. And what did they find? ASIC found that lenders have been falling short of their responsible lending obligations in the provision of interest-only loans. Lenders are often failing to consider whether an interest-only loan will meet a consumer's needs, particularly in the medium to long term. So it's important that we understand interest-only loans and their risk. And basically, well, I'm not going to give any financial advice, but I personally would avoid them. Let's understand what they are and how they work, just so we can understand how they operate in the world. What's happening here is we have a balance that is never changing. The payments that we make are equaling our interest rates. So we have our $620K that we owe. We increase with interest. Usually we would pay more to drop the principal of our loan, but here we only pay the amount that we just owed. And that means that 20 years from now, I'm still going to owe $620,000. Now, why would someone do that? Why would they never want to pay off their loan? The thought process, and the reason why some people do it, is they say, I'm an investor. Usually investors do this. They say, I'm going to buy this property. It's going to go up in value, and then I'm going to sell it for much more later on. So even though I never pay off the loan, when I sell it, I'll sell it for more, and then I can pay it off with that. What's the risk of that? The risk is if the market crashes. If the market crashes, you've never paid off any of your loan, and suddenly, you're going to sell your house for $400,000, but you still owe $620,000. So you're out of pocket $200K. Where are you going to find that from? That's a quick summary of why these things are risky, because you never pay off the principal, you are exposed to a falling market. Whereas in most of the loans that we do, our standard reducing balance loans, we're going to pay off the principal, and usually it's a home that we live in. And even though the market does fall a little bit, well, we've paid off that principal, and so we can sort of stay strong in a falling market. All right, that's the idea on interest-only loans. See you next time. Right, there are some skills we have to learn today. Interest-only loans, 2 key skills. What is it? And can we find the payment, the interest rate, and the principal? All right, what is an interest-only loan? It's one where the payment matches the interest. We've just looked at that idea. If you didn't watch the intro slide, watch the intro slide, people, right? Our balance never drops. Our balance never drops because we're only ever paying off the interest. So we can see those ideas summarized nicely here, and we're going to use it to do a few calculations. But to do some other calculations, we're going to need a formula. This is the formula for the payment on an interest-only loan. And if you think about it, you'll see that it's very similar. In fact, it's identical to the formula we had for finding the interest part of the amortization table, or the interest on a loan. We took our previous balance, we took our annual interest rate, and we divided it by the number of compounding periods per year. Often it was like X we used, but X and N are the same thing, interchangeable. So it would be our annual rate divided by 12 divided by 100. Now that's the formula to calculate the interest that we owe. And if you think about how an interest-only loan is defined, the payments are equal to the interest, like they're the same thing. And that's why this is the formula for the payment as well. Let's use these ideas, and we're going to go and solve some questions. For some of them, we'll be able to use this. For some of them, we'll have to use this. All right, calculate periodic payment required for interest-only loan, $235,000 with 2.9% interest rate. Let's see if we can find a solver for this question. 2.9%. Present value, I take this money. 1, 2, 3. Too many zeros. One back. I don't know why. Every time. Payment, I don't know. Future value, interest only. I don't pay back. I still owe money. Minus this. Cool. I want to press enter, but I can't because it's not need n. N interesting. N is interesting. This situation I've just typed in works for every single scenario, right? After 1 month, I have this, I owe this, I have this, I owe this. So it doesn't matter. I can take n as 1, and I get a value there, and I can take n as 20, and I get the same value as well. Oh, so we see that our payment is $567, 91, 66666, 567, 92 cents. What if I wanted to solve that using the formula? D equals R, number of payments per year, 12, times the borrowing amount. R is our annual interest rate, 2.9. So if we did that, let's check it. Beautiful, we get the exact same thing. So in this case, for finding the payment, we can use either the calculator or the formula. All right, those are the KDs for interest-only loans. See you next time for amortizing annuities. If I study general, yabba dibby 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 dum, all day long I'd NIPV PMT FV CPY PPY. Hi! Welcome everyone to today's lesson. We're going to be looking at amortizing annuities. And these annuities are going to be the wonderful financial tool that will hopefully provide you with a good lifestyle in retirement. You work during your life, we work to save up some money, to provide for our lifestyles, to hopefully give us something to live off when we retire, and perhaps to pass on to future generations. If you're running your own business and you don't have a direct employer, it's really important that you pay into your own super to build up that wealth to give you a happy retirement. We're going to be looking at amortizing annuities, and I've chosen the term amortizing annuities to help distinguish it from a few different other realms of annuities. So just to briefly give you an idea, one of the types of an annuity is a perpetuity, one that never changes in balance over time. So we're not looking at that right now, okay? Another time we use the word annuity is with something called an annuity investment. And that's when we're building up our superannuation over our working life, right? That is called an annuity investment, right? This is called a perpetuity. But once we retire, the balance inside our annuity starts to drop down, right? And the idea of something amortizing is the idea of it reducing in value over time with regular payments. And in the study design, we can use this term, the amortization of an annuity. And here, in this lesson, when we talk about amortizing annuities, we're talking about this product paying you out money during your retirement, so dropping down in value over time. And there are 3 key skills in today's lesson: recurrence relations, the amortization table, and using the finance solver. All right, we spoke a bit about the idea of an amortizing annuity, but let's look into it with the mathematics to help understand what's going on. We start off with 500K. So we're at the point of our retirement. Yeah, we've been saving up money all of our lives. Bang, 500K is there. It's sort of sitting with this superannuation company. What do we work out? Let's work out the value of our super after 1 month of retirement. Okay, so V1 would equal 1.005 multiplied by 500,000. And if you wanted to know what that was, that would be $502,500. So because it's sitting in a financial product, it's like an investment. It's earning interest and it's growing in value. That's really good. But hang on, we're living in retirement here and we need some money to live off. So yeah, it grows in value, but then boom, the money comes back to us. It comes out to us and we can use that to spend and live on our lives. So that's going to cause the balance of our superannuation to drop. It's going to drop to $499,280. Now we could do the same thing for the next one. And as you will see, if you remember back to a few of the examples we did with reducing balance loans, the exact same thing is happening, right? The value of the balance goes up with interest, and then it drops down with the payment. What's the difference between a reducing balance loan and an amortizing annuity? The only difference is the direction of where the money is going. In a reducing balance loan, the bank gives me the money and I make the payments. In an amortizing annuity for my superannuation, I put my money into the superannuation. It's like at the beginning of my retirement, it's like, hey, super, here's the money, use it, right? And then they give me the payments. So mathematically, the exact same thing happens with the numbers. We just have to think about who is giving and who is receiving. The key ideas are summarized over here. Let's have a go with a practice question. All right, the amortization table for an amortizing annuity looks very, very similar to a reducing balance loan. At the end, we're going to hit 0, okay? Our payments are regular, they're the same, but just like the reducing balance loan, we might have an adjustment in our final payment. And the skills we looked at for the final payment in the reducing balance loans lesson part 2, you can also use to work with final payments with annuities as well. We have here a few formulas that connect the ideas of the annual interest rate, principal reduction, and total interest. Some of these might come up in the examples to come. All right, let's dive into some calculations to see where some of these numbers come from. If you've seen the equivalent slide in reducing balance loans, feel free to skip this because the calculations will be exactly the same. But let's say you've just opened up this video, you want to find out a little bit more about these annuities. I'll show you now what this amortization table does and how it works. Okay, so the first thing we want to be able to do is calculate our interest. And that's going to come from our 6% per annum. Our interest calculation is 6% per annum, but each row in the table is a month, right? Altogether we have 300 divided by 12, 25 years. So 300 months altogether. So if I want the interest in one row, that's a monthly interest rate, I'm going to have to divide my annual rate by 12. We divide it by 100 to get to a decimal. We multiply it by the balance, like the prior balance. When we had $500,000, now what's happening? We're growing that $500,000 with the interest. So we look back to the prior row. We get 500, 1, 2, 3. And that gives us $2,500. Okay, now our payments are $3,222. What's happening? A section of that payment is basically covering the interest, and a section of that payment is coming from the balance. In the world of loans, we were giving the payments and we were sort of paying off a bit of the interest, and we were also paying off our loan. In the world of these annuities, we're receiving the payments. So what does it mean that it's made up of two parts? Let me show you what's going on. We start off with $500,000. That's what exists in our superannuation, okay? Then at the end of 1 month, the balance grows with interest. Now our net worth is higher, right? $502,500. Then the payment comes out and we drop down to our new balance, right? 499, whatever that is. Yep. So our interest was this, okay? The payment made was this. If I have received this payment of $3,222 to live off, it didn't all come from the interest. Part of it came from the principal that was sitting in my superannuation. and that's the principal reduction over there. So that's how we work out our principal reduction. It's our payment minus the interest. In this case, $3,222 minus the interest from that month, which was $2,500. And that's what gives us the $722, which was taken out of our balance in that month. As you can see, if you keep doing that, balances are taken out more and more and more and more and more, and eventually our principal drops to zero. Principal drops to zero, we have no more money to live off. Hopefully, our financial planning was right, and that 300 months took us from our retirement up until our death. I mean, I don't want to die, let's live forever, but we want to plan accordingly. This new balance, what is this new balance, right? We run to get to our new balance. Well, that's our previous balance minus our principal reduction. All right, let's look at the annuity with a finance solver. Okay, if we're talking about an annuity that drops down to zero at the end of its life, right? That drops to zero, then our future value will be zero. What about if we paused halfway? If we sort of stopped halfway through the annuity, we said, thanks, superannuation, I'm gonna just leave you there. I'd like to actually take all the money out. Well, in that case, all the money would come to us. We'd be like, yeah, very good, thank you. No more payments from you. Give me the money. I'm going to do my own thing. Great, so that's a positive value. The payments are also positive because they're coming to us as well. But the present value at the very beginning, when we sort of set this up with the superannuation fund, or we set this up with the financial company, we say, all right, here's the lump sum of money, now give me payments. We give the money, the principal value to that company. And that's why PV is negative. Does that make sense? Let's just make a little note here. That's zero at the end, or it would be positive if it happened in the middle. All right, those are the key ideas for the amortizing annuity. Our present value negative, our payments are positive, and our future value is either zero or positive, depending if we're at the end or in the middle of the process. And I'll see you next time for Perpetuities.
If I study general, yabba dibby 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 dum, all day long I'd NIPVPMT FVPPY CPY. Welcome everyone to today's lesson on perpetuities. What is a perpetuity? For most of us, when we retire, we have our superannuation, and we need to live off that, and it's going to make us regular payments to live off. And those payments will be more than the interest earned, and eventually that superannuation will drop down to zero. We'll time it so that we basically have that luxury as long as we live. But if you're lucky enough, you might be able to save up enough such that your payment's never going to be more than the interest rate, and you're able to pass this asset on to your grandchildren, and that could be a nice thing. Let's go and learn about this, and let's see how it works. Perpetuities are two key skills: defining a perpetuity, finding the payment, the interest rate, and the principal. So let's look and understand a bit about what's happening. This amortization table before you is not of a perpetuity. It's of a standard annuity. It starts with a certain amount of money. We get our regular payments. They are bigger than the interest rate. They're larger than the interest rate, which is causing a reduction of principal. It's causing the balance to go down over time, eventually to zero. Does that make sense? What if you came along and you decided, hang on, I don't need $1,703 a month to live off. I can manage with $1,375. Look at this. If I just made my payment equal to the very first interest, then I wouldn't reduce my balance at all. It wouldn't drop. It would stay as it was. And then the next month, all right, I would earn an interest of $1,375, and I would only take out $1,375, and I can do that again and again and again forever. I could live for 30 years like this, and I would still have the balance left at the very end. Now, if I can live off this, great, and then I can pass on this balance to future generations. If $1,375 is not enough to live off, and that could well be the case, then my balance is going to drop over time, and that is okay. Just to give another idea of what this could represent, it could also represent a scholarship at a university. Let's say you've been a very successful dancer, and you've earned millions of dollars across your dancing career. You decide to give to your local university a gift of $300,000 to award the annual Superb Dancer of the Year student to the best Superb Dancer of the Year. Then every year, this balance would grow $1,375, and then it could pay that money out again. And then the next year it would grow, and then it would pay it out. And what you're doing in giving this gift of a very large money is basically hoping that this thing could pay out forever. This can go well past 360 because you're never dropping the balance at all. Does that make sense? All right, so what can we see? Originally, when we put the money in the financial institution or in the university, it is negative. We're giving it away. At the end, if we want to do something else with the money, well, we'll have to get the money back. It's coming to us. It's positive. Our payments, yeah, they're coming. My investment is paying me all this money in retirement. Yeah, that's positive. What about N? Well, N can be any value. Just like with our interest-only loans, and if you think about this, you'll see that this financial product is exactly the same as an interest-only loan, just the direction of things is different. But N can be any value. We also have this formula over here. And if you haven't seen the interest-only loan lesson, let me explain where it came from. If you have, just skip to the end of the slide. We know that our payments are equal to the interest earned. Okay, and the way we worked out interest in all previous lessons is we said, we'll take our annual interest rate, we'll divide it by the number of compounding periods a year. Sometimes we used an X, but it's the same thing with an N, right? Maybe it was 12 periods a year, whatever it was. Divide that by 100, we multiply that by the initial amount. So if it's like if I had 6% a year per month, times that by the initial investment of $500,000, that was the interest that we earned on the investment. However, in this case of a perpetuity, the payment we receive is equal to the interest. And therefore, this formula for interest is the same formula for the payment. Does that make sense? That makes sense? We're doing the same thing we did for interest because the payments are the same as the interest. All right, we're going to go and do some examples with this. For some of the examples, the formula will work. For some of the examples, the finance level will work. And hopefully through the examples, you'll get an understanding of when to use which one. All right, a wealthy alumnus sets up a scholarship for the Edrolo University. Big dreams, Edrolo. To the student who has the most video watching potential every year. How much do you binge? The initial principal is $235. We know the annual interest rate. And we're told these payments are going to be made forever. Basically, this is a perpetuity. Very nice. What's the monthly payment that's going to go to this student? Right? If you invest $235K, you want to last forever. How much money would your student get every year? Let's have a look. What do we know? We know the initial present value is negative 235. It's negative because we give it, hey, Edrolo University, take this money, do something with it. In the end, if I was like, all right, Edrolo, no more prizes, give me the money back, it would come back to me at 235 in a positive way. The annual interest rate, which is basically gives us the interest we're going to pay out, is 2.9. And for N, I can choose any value I want because this step is happening the same at every month. It happened at the first month, the second month, the third month, blah, 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 all the months. So we press enter on this. It was $567. And just to prove the idea that N doesn't matter, let's try 126. We get the exact same thing. So the monthly payment, $567.92 if we're rounding to the nearest cents. What if you wanted to use the formula? All right, so our regular payment is going to be our annual interest rate divided by the number of compounding periods a year over 100 times by our initial investment, V0. Okay, in this case, 2.9 out of 12, because we've got monthly payments, out of 100 times by 235,000. And you would get the same thing, $567 rounded 92 cents. All right, those are all the key ideas for the perpetuity. Remember that for N, you can use any whole number. Interest rate, the present value, we give the money. It's negative. Payments come to us. At the end, if we close up shop, the money would come to us as well. I'll see you next time for annuity investments. All right, today's lesson is all about compound interest investments. This is Lisa. She's super happy because she has worked out how to be a millionaire in retirement. Well done, Lisa. Would you like to know how she did it? Well, watch this lesson and find out. We're looking at annuity investments today, which are also known as compound interest investments. And let's just establish a bit of the terminology here because people often get very confused. Usually when we come across the idea of an annuity, it's the idea where we put money into our super fund and then in retirement, our super fund is paying it out to us. It's something that drops in value over time. This one we've called an amortising annuity. Okay, there's another type of annuity called a perpetuity, and that's where the payments are equal to the interest rate. So instead of dropping down over time, we just maintain a straight line. Usually all these things are represented with dots because they only happen like once every month rather than continuously over time. But the dots or the lines, for my purposes, don't matter too much. Okay, so that's a perpetuity. For today's lesson, we're looking at something that is neither of those two. We're looking at how do we build up to get this amortising annuity in our retirement. Over your working life, you're going to be putting money into super, and that's going to grow with interest over time, and you're also going to be adding regular payments. So this split here is the difference between the annuities we've seen so far and the ones we're looking at today. This is an annuity investment. It's also called a compound interest investment, and it happens when we add more money to an investment account, which happens over our working life. We're depositing in. Later on, we've retired and we withdraw on that money. They're both called annuities because they're both part of this bigger concept called superannuation. So we're going to look at three key skills: the recurrence relation of this annuity investment, the amortization table, and the finance solver. All right, let's look at the recurrence relation for a compound interest investment. We can see that there's something different about this one that is different from all of the other financial products we've seen before. Previously, our balance grew with interest, and then we reduced our balance with a payment, right? You had a loan, the amount we owe goes up, but we reduce that down and we drop it with a payment. Here, the payment is positive because not only is our balance, our investment growing with interest, we're also adding in regular payments to make it grow even more. So let's use this recurrence relation to sort of mathematically feel and see what's going on. We take our 1.0045, we multiply it by $70,000. That's the growth from interest. And if we did that, we would get $70,315. But not only do we grow to that, we also add in an extra $1,000 so that at the end of the first month, our asset, our investment is worth $71,315. And you can do the same thing for the second month. And if you look closely at this second installment, you'll see that the interest earned was even more than the previous one. Why is that? Because we're earning interest not only on like just the value of the previous asset, we're also earning interest on the extra payments that we did. So this compound interest investment, this annuity investment, is even stronger than a standard compound interest investment. Back in chapter 5, we spoke about compound interest. We just had a value that was going up and it looked geometric because as it grew more because it was bigger. Here, that is also happening, but not only is it growing from its own interest, it's also growing from the payments as well. Is that making sense? Like there are two things contributing to growth here. One, just the general growth in interest, and two, all these payments that we're putting in. So we're getting like super powerful growth. And that's what happens with your superannuation. As you work in your life, you put your money in, it grows with interest. And also, every time you add money, you're going to make it grow a little bit more because you get calculating interest on what you've just added. The key ideas are summarized over here. Let's see if you have a feeling of this concept and this recurrence relation to solve a few questions. All right, this is what the amortization table of these annuity investments look like. We start with our balance. We add interest, right? Just like our amortizing annuity, the thing that pays us in retirement, like the interest is helping to grow the balance. But unlike the amortizing annuity, the thing in retirement, the payment is not coming out of the balance. Like when you retire, your value of your asset grows, but then it shrinks because it's paying you out money. Here, it's growing, and then you're contributing another payment, so it's growing even more. So actually the sum of this and this is what gives us the principal addition. You'll see this word is different to all the other times we've labeled this column. It was always called a principal reduction because the value fell. Here it's a principal addition, and therefore the principal addition here is the payment plus the interest, and the formula there is a little bit different to what you've seen in the previous lessons. And we can tell just by looking at the table that it is this kind of product. It's a compound interest investment because the balance is going up over time. Cool? All right, you've seen these kinds of calculations before, but let's reinforce them and just get a good feel of how they work with these compound interest investments. If I wanted to work out what this interest value was, Well, I would take my annual interest rate of 5.4%. We divide it by the number of compounds per year, which in this case is 12. We divide it by 100. And we times it by the previous balance, right? We're taking in interest of the previous balance. That's what's growing. $70,000. If we get that, that is $315. And that is our interest. Cool. Now, I am also choosing to contribute every month another $1,000. So in this case, our principal addition is the sum of those two. It's a nice and easy calculation. And the change in the balance is going to be our balance plus the addition. When it was reduction, we minus it. When it's addition, we add it. Cool. All right, what about our good friend, the finance solver? How will things play out here? Well, my present value is going to be negative because I'm putting the money into the account. Like I'm starting off my investment with, what was in the last example, $15,000? Put it into the bank, negative. The payments in this case are also negative because I'm adding extra payments in, yeah? That's going to result, though, in a wonderful future value that is going to come back to me, and that's why it's going to be positive. All right, everyone, those are the key ideas from today's lesson. We have our present value, which is negative, and our payments, which are negative, because both of them we're putting into the investment, they're coming away from us. But we get a nice big future value positive at the end that comes back. We've got some key formulas, we've got amortization tables. Coming up next is a progress check, a topic test, and that's basically the end of financial maths. I've really enjoyed going with you on this journey, everyone. Good luck for the rest of general maths and good luck for life. If you think about over the course of the last 6 chapters, you've learned a hell of a lot, so well done, and I'll see you on the flip side.